The same is true for the labyrinthine patterns formed by the green or black scales of the ocellated lizard. A multidisciplinary team from the University of Geneva, UNIGE, explains, thanks to a very simple mathematical equation, the complexity of the system that generates these patterns. These results are published in the journal Physical Review Letters. A complex system is composed of several elements, sometimes only two, whose local interactions lead to global properties that are difficult to predict. The result of a complex system will not be the sum of these elements taken separately, since the interactions between them will generate an unexpected behavior of the whole. The group of Michel Milinković, professor at the Department of Genetics and Evolution, and Stanislav Smirnov, professor at the section of mathematics of the Faculty of Science of the UNIGE, have been interested in the complexity of the distribution of colored scales on the skin of ocellated lizard. This is a computing system invented in 1948 by the mathematician John von Neumann, in which each element changes its state according to the states of the neighboring elements, explains Stanislav Smirnov. In the case of the ocellated lizard, the scales change state, green or black, depending on the colors of their neighbors according to a precise mathematical rule. The road to simplicity. Szabolcs-Székely, a theoretical physicist in Michel Milinković's laboratory, teamed up with the two professors to determine whether this change in the color of the scales could obey an even simpler mathematical law. The researchers thus turned to the lens-Ising model developed in the 1920s to describe the behavior of magnetic particles that possess spontaneous magnetization. The particles can be in two different states, +1 or -1, and interact only with their first neighbors. The elegance of the lens-Ising model is that it describes these dynamics using a single equation with only two parameters: the energy of the aligned or misaligned neighbors, and the energy of an external magnetic field that tends to push all particles toward the +1 or -1 state, explains Szabolcs. More precisely, they adapted the lens-Ising model, usually organized on a square lattice, to the hexagonal lattice of skin scales. At a given average energy, the lens-Ising model favors the formation of all state configurations of magnetic particles corresponding to this same energy. In the case of the ocellated lizard, the process of color change favors the formation of all distributions of green and black scales that each time result in a labyrinthine pattern, and not in lines, spots, circles, or single-colored areas. These patterns are generated by a complex system that yet can be simplified as a single equation, where what matters is not the precise location of the green and black scales, but the general appearance of the final patterns, enthuses Michel Milinković. Each animal will have a different precise location of its green and black scales, but all of these alternative patterns will have a similar appearance, i.e., a very similar energy, in the lens-Ising model, giving these different animals equivalent chances of survival. https://ift. tt. 3 hdbgxy. Access January 27, 2022. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.